Yeah, it started, I hope. So you live in East Hartford, or you're somewhere nearby? Okay.
Yeah, we moved to East Hartford, or well, Hartford area last July. Before that, Dayton, Ohio for 12 or 13 years.
I see, long time. Yeah.
Yeah. Yeah. It was,
I was in East Hartford last year, sometime in June. Yeah, last June, in fact, or July. I don't remember.
Okay.
Yeah, I was meeting Kevin, and I think Sonia was also there.
Yeah. Did you give a presentation at
yes.
One of the all? Yeah.
Yes.
All right. Now I recognize you. Yeah. Okay. Perfect.
Yeah, I think, yeah, it looks different on the camera now. And I'll probably come back again in June. I had written to Kevin, and I will be visiting Sanjay's consortium meeting at Stony Brook. So I thought I will again pay you a visit.
Yeah, great. Look forward to it.
Yeah.
Dipankar Banerjee's invited me out to India, and I thought I'd had it all nailed down, and then we went on a travel break, so nobody's traveling unless it's absolutely critical for customer visits.
I heard. Yes. Yeah, Pratt has had travel embargo, I guess. I'm so sorry.
Yeah.
Yeah, so we just had, we concluded the electron microscopy conference today, in fact. So we had 3 days of the conference, and Dipankar was here also.
Oh, nice.
And so were many other microscopists, at least from across the country, and lots from Germany and from China and so on. A few from the US. Yeah.
Excellent.
Yeah, since it's 6:02, we will get started and people will trickle in if that's okay. So let me introduce you formally, and then we'll get started. Yeah.
Sure.
Yeah, welcome everyone to the Indian Structural Integrity Society webinar series. Today we have Dr. Adam Pilchak from Materials and Processes Division at Pratt & Whitney, East Hartford. He's a senior fellow there, and he will be talking to us about characterizing and modeling the precursors to coarse grain growth in Beta-Annealed Ti-6-4. Adam is a classically trained metallurgist with expertise in composition, process, microstructure, and property relationships for metallic materials. He promotes the use of advanced characterization methods and computational modeling tools to understand the fundamental mechanisms that drive material behavior and how they can be manipulated by thermomechanical processing to achieve the right balance of properties, something which I'm sure lots of traditional metallurgists identify with. He's a strong advocate for integrated computational materials engineering, or ICME as it is known as, and model-based material definitions. He has participated in multiple RCCA investigations and is currently leading an internal effort under the Additive Manufacturing IPMT to streamline the airworthiness processes for AM components in commercial and military engines. Adam is active in multiple professional societies, including KMS and ASM, and represents the Alloys Group in the jet engine, nickel and titanium quality committees under the auspices of the FAA. He's also committed to educating the future workforce. In this capacity, he has served on numerous PhD committees for leading institutions and teaches a course on fatigue and fracture of materials at Johns Hopkins University. Prior to joining Pratt & Whitney, Adam was a senior materials research engineer in the Air Force Research Laboratories Materials and Manufacturing Directorate, and held several roles during his tenure, including research lead for the metallic materials and processes team and the turbine engine sustainment lead. In these roles, he conceived, executed, and managed both basic and applied R&D programs related to microstructure, characterization tools, alloy development, non-destructive characterization of microstructure, process modeling, and behavior and life prediction. So in some aspects, I think we share the general concept of fracture and fatigue teaching. This is what I do in IIT Bombay as well. And of course, overall, in looking at both the aerospace materials as well. So yeah, looking forward to listening to you, Adam. Thank you so much.
Yeah, great. Thank you. Greatly appreciate the invitation as well. So first off, I think everyone will notice that the slide here has Air Force Research Lab on it instead of Pratt and Whitney. So in trying to think about what would be good content to cover here based on kind of what Deepa and I had talked about initially, there wasn't really anything complete and comprehensive enough that I'd done at Pratt and Whitney quite yet, since I'd only been there about a year and a half at this point. So I thought this was a nice story, though, that tied together, some fundamental issue that was happening in the manufacturing supply chain, how we used a little, forensic metallurgy, so to speak, to uncover what the root cause was leading to the issue, and then how we did some laboratory trials supplemented by various computational modeling techniques, and then ultimately scaled that up to support production parts again. So the issue was that several airframe structural components were forming these abnormally large grains once they went into the beta-annealing process. And the grains are huge, like the size of your thumb, or maybe even two of them in some cases. And so as everyone knows, large grains tend to be bad for strength and fatigue properties and things. And so we were called in to try to understand what the source of that issue was and how we might overcome it. So this was a quite long project, and so there's a whole cast of people that helped along the way. So I've got their names listed there. I won't go through them in great detail, but it was a variety of both government, Air Force, research lab employees, on-site contractors, and then we partnered with Arconic, who's a primary metal producer for structural components, as well as Lockheed Martin, who's the airframer, in terms of trying to scale up and make sure that the things that we did in the laboratory still applied in the production environment, and ultimately tried to make some useful recommendations for how supply chain could practically overcome this issue. So just a brief outline, right? I'll cover a little bit of the background motivation, talk about what happens when you go from, say, the two-phase field, and in the very earliest stages of dissolving that secondary phase that's pinning the grain boundaries, what happens to the underlying beta phase structure. And then we will look at some Monte Carlo modeling approaches that were used to try to understand some of the sources for the abnormal grain growth. Think a little bit about the effect of strain path on the formation of these abnormally large grains, and then talk a bit about some of the laboratory trials that we performed and used, both continuum FEM modeling as well as crystal plasticity modeling, to try to set some bounds and limits on some of the critical process parameters that are, again, driving this behavior. And then at the very end, I think I've got one or two slides maybe on the scale up effort. So titanium's used obviously extensively throughout aerospace industry, both civil and military engine components. Probably last time I read the stat, it was roughly 80% of the titanium that was in use across the industry was the Ti-6-4 alloy, used both in turbine engine components, kind of up in the front cold section, maybe certainly the fans, and then the front stages of the low pressure compressor, and then also used extensively in airframe structures. I'm biased, but I think it's a beautiful material. There's a huge range of accessible microstructures depending on the processing routes. So temperatures you deform at, the strain paths you apply to work the metal, and then the subsequent cooling rates from those and or solution heat treats as necessary. Among this myriad of microstructures, there's two that are kind of the most common. So in the upper right there, we're looking at the bimodal microstructure, where you've got a mixture of these, excuse me, equiaxed alpha particles, and then they're set in a matrix of what's often called transform beta. So it's a mixture of alternating alpha and beta laths. Alpha phase is hexagonal close packed, and the beta phase is body centered cubic. The vast majority of the microstructure, 93%, something like that, is the alpha phase. So it definitely dominates the mechanical response. And that condition is known to be a really good balance of strength, ductility, and fatigue performance. But compared to the other microstructure below the Beta-Annealed condition, bimodal does suffer a little bit in terms of damage tolerance, and specifically crack growth rate and toughness. And so many of the airframe components then are utilize this beta annealing approach, where you can form relatively large colony-like microstructures, and they have the benefit of causing a lot of crack path or crack tip deflection, bifurcation, secondary cracking, and things, all of which reduce growth rates and contribute to the overall toughness. So Ti-6-4 has been used since the late 50s, early 60s was when they started manufacturing components, and it's this Beta-Annealed condition has what I would consider a relatively simple processing route, and this is probably oversimplified here, but essentially what happens is you cast and solidify an ingot, and then that goes through a series of steps that we'll just loosely call homogenization here to turn it into a billet. So there could be many steps in there, multiple upsets, draws, reheats, and things, but eventually the converter produces typically a cylindrical billet. Sometimes they're square shapes, roughly say 8 to 14 inches in diameter, and then those are used for subsequent processes to produce useful components. So that's kind of where we'll pick this up. And so for the Beta-Annealed condition, typically one would actually do the forging process in the alpha beta phase field and in step 2 here. And then once that's done and cools down, it goes into another furnace where it's taken above the beta transist for a period of time and cooled as quickly as possible, generally to try to balance the colony size. But ultimately, because of the low thermal conductivity of titanium, you're generally limited by that thermal diffusivity, and so most components, at least within or greater than about 3/4 of an inch from the surface, end up forming these relatively large colony structures. And then finally goes through some low temperature annealing step just to relieve any residual stresses and things that might form. So very simple. Been doing it for decades, yet sometimes, very periodically, when cut-ups are performed, you'll find these large clusters of really coarse grains. And so showing a cross-section from an actual structural forging there, and at a little higher mag in the inside, you can see this big region of really large grains, so large prior beta grains, and then they have correspondingly very large alpha colonies within there. Interestingly, this is usually surrounded by what we're calling the fine grain halo here. So very stark contrast and pretty sharp interface between these really coarse grains and really fine ones. And we'll get into the source of that in a little bit. But then eventually you get away from there and you get the typical expected microstructure. And so in this case, the nominal beta grain sizes are of the order of a millimeter or so, and that's expected. One of the problems is you can't detect these until you go through the whole process of producing the billet, forging it into a part, heat treating, and then you spend all the money to get down to this final machine state, and then that's when the grains are uncovered. There's auxiliary efforts looking at how can you do this non-destructively, and so I think there is some actual ultrasonic response that differentiates the fine grained regions from the coarse ones. So there may be a path there, but nothing that's kind of production ready at this time. And so this has resulted in lots of parts being scrapped. And at the time we were working on it, there seemed to be an uptick in the number of rejects due to this condition. And also at the time, and actually persisting into today, the lead times to get titanium billet are quite long, approaching a year in some cases, and so there's programs that are waiting for these forgings, and then they get the news that they're non-conforming and have to wait a whole lot longer. In the upper right here, showing a numbers are removed here, but showing a kind of classical fatigue crack growth curve. So DA, DN, crack extension per unit cycle. And on the bottom here is delta K, stress intensity factor range, which you can think of as the driving force for crack growth. A lot of the airframe structural components are designed and managed to at least in the Air Force, damage tolerance requirement. So the first thing people are ultimately interested in is what's the effect on the crack growth rate. If you cut compact tension specimens out and you run conventional fatigue crack growth curves, you find there's maybe a small debit between, say, a typical conforming microstructure and what you might get with the abnormal grain growth. And so that's not too bad. People can live with that, alter inspection intervals. But what this approach doesn't consider is what's known as the small crack effect. And so that's what I've kind of just sketched in this reddish bubble there. And the small crack effect is interesting when real cracks form and they're naturally initiated. They form kind of with microstructural dimensions. So if one of these large beta grains with its corresponding large colony inside forms a fatigue crack initiation site, the crack can grow essentially unimpeded for quite long distances, physically large distances. And some of the attributes of small crack growth are that they can grow at values of delta K that are below the so-called threshold for long cracks. They also grow at faster rates than their long crack counterparts for stress intensity ranges that are greater than delta K threshold. And this kind of accelerated rapid growth can persist up to many microstructural dimensions. The kind of rule of thumb is somewhere between 5 and 10. And so now if we have grains that are of the order of several millimeters, and I extend that out to 5 or 10 microstructural dimensions, we can have multi-millimeter sized cracks develop before they follow the classical design curves quite well. And so therein lies the concern with respect to structural integrity, and that's why we needed to figure out what was happening. So that was kind of where the team I worked with got brought in. Oops, sorry, I'm trying to move these. Not letting me move my. Sorry. Okay, there we go. So yeah, we got brought in, somewhere around that time, and received a section of one of these structural forgings, and immediately took it to the SCM, did some backscatter electron imaging work, as well as some EBSD work right around an area that contained some of the coarse grains, some of that fine grain halo, as well as some of the nominal conforming microstructure. And so this is the measured alpha phase data set that was collected. So you can see the large beta grain popping in down here. What we're calling the fine grain halo is this mixture of purples and greens, so nominally 2 orientations. And then when you get out to the nominal microstructure, typical 1 millimeter or so beta grain size is filled with colonies. You see a variety of different colors indicating kind of a little more random texture, though it's not perfectly random. During my dissertation work, I developed a code to do that inverse calculation, so taking the measured alpha phase orientations and knowing the orientation relationship between the alpha and the beta phase, it's possible to recalculate what the high temp beta phase must have looked like to produce the microstructure that we ultimately observed at room temperature. So that's what we've done on the bottom here. And the first thing that jumps out is this region A, what was all of these greens and purple colors here. reconstructs back to almost essentially a single orientation that's comprised of a whole bunch of low misorientation subgrains. And so this is the corresponding pole figure for that. You essentially see a cube-like texture there, but again, there is some distribution about that average kind of nominal cube orientation. When we get out to region B, we do see some remnants of that cube orientation still. Texture intensity has fallen quite a bit, and then the size of the spots on the pole figures, so the distribution of orientations is also a little bit larger. So this was a really interesting data set to look at, because about 5 or 6, 7 years before that, working with my colleague Lee Semyatin, we were attempting to do really short duration beta annealing trials on rolled plate material to produce a fine recrystallized beta grain size to study the effect of grain size on development of transformation textures. And when we did that, we were beta annealing for 5 seconds, 10 seconds, 30 seconds, a minute, 2 minutes, very short durations. And so we had this series of snapshots of what was happening at the earliest stages of recrystallization, and this like single crystal-like texture in region A really struck me as something that I'd seen before. And so in that original work looking at the rolled plate material, we had basically characterized all of these intermediate annealing steps, but because they weren't fully recrystallized, we put all of it back in the drawer. The data, just sat on a hard drive for several years, and we thought they were, we thought it was a failed experiment basically, because we didn't get the microstructure that we wanted for for the remainder of the investigation. But after seeing similar features on the structural forgings, we dusted off all of the old data and all the old samples, and started looking at it again. So here's an example of one of those what we thought were failed experiments, but turned out to be really useful. So in that work, we had these flat plate-like specimens, and we were heating them up, holding them just below the beta transit for a couple minutes to stabilize the structure, and then we would flash the microstructure, or flash the sample above the beta transits before cooling at around 155 C per minute. And as I said, we had different times up there ranging from about 10 seconds to 750. And so a couple things I want to point out here. So at room temperature prior to testing, on the lower left here, this is what the alpha phase orientation map looks like. So if anyone's familiar with the term microtexture, right, there is some degree of microtexture in the material. But what I think is the most interesting is if you zoom in really, really far, do very high spatial resolution mapping to the point where you can directly measure the beta phase, we see a whole range of different orientations. So I've got some, reds, blues, pinks, greens, yellows, so a variety of underlying BCC orientations. However, well, and I'll say one other thing. The classical theory, things that have been measured by, say, synchrotron or neutron diffraction heating experiments, would say that as the alpha phase dissolves, the beta phase that's already present tends to grow in size. So you don't like formally recrystallize and get new beta orientations upon heating. So what that would suggest is if, in your mind, you expand these colors out until, so all the black is alpha, right? So that's dissolving. And as you expand these different colors out that represent the beta orientations, eventually you would get contact between, say, blues and reds, pinks and greens, yellows and purples. And so you would expect that when you get just above the beta transit, you would have this, nominally random beta phase texture. But what we saw at the shortest annealing times, and I'll show you in a moment that this persists over several minutes, we saw that all of these, all the beta phase orientations disappeared except for this cube-like texture. And there's some reasons for that we'll get into in a little bit. So This was, again, the example of one after 30 seconds, and you'll recognize that a lot of this green and purple orientations are very similar to what we saw in that fine-grained halo earlier. But in some locations, you do see evidence of different alpha phase orientations. And so these are, so-called recrystallized grains. The reconstructed beta map is on the bottom, and then the corresponding area here, you can see that indeed they are highly misoriented with respect to the red kind of subgrain matrix. If we now just take some line profiles through that, so line A here, I'm just cutting through all of that subgrain matrix. So you see a whole bunch of misorientations that are, say, less than 15 degrees or so. In line B, where I'm cutting through a couple of these recrystallized grains, then I find when I'm in the matrix, I have a lot of these local misorientations. When I get inside of that recrystallized grain, misorientation drops to near zero, indicating that it's relatively recrystallized, strain-free. And the same thing happens when I cut through this larger yellow one over on this side. So for the purposes of this work, we drew the line at 15 degrees as a way to just classify what was recrystallized versus what is not. That was kind of aided by looking at just the misorientation angle distribution of the subgrains only, which show a peak around 7-8 degrees and then decay rapidly toward about 15. And so we drew that as our distinction for the subsequent work. All right, so here's a couple snapshots of the evolution over time. So it's just 4 of them, but 10 seconds, right around a minute, 100 and 210 seconds. And so what we found was that at early stages, we would, even as early as 10 seconds, we saw some fraction of grains that had recrystallized. The subgrain size at that time was around 15 microns. Average misorientation was around 6 in those subgrains. With additional annealing time, you get a larger fraction of recrystallized grains. The recrystallized grain size increases, but the subgrains remain relatively stagnant. So even all the way up to about 400 seconds, the subgrains had only coarsened by a factor of 2, with the average misorientation staying pretty close to where it was. However, as you can see here, the recrystallized grain size got as large as a millimeter or so. So initially, these recrystallized grains are growing into a matrix of subgrains, and then later, eventually, you get impingement between the recrystallized grains and transitions to more of, say, like a curvature-controlled grain growth phenomena. So we use JMAC kinetics to analyze the recrystallization mechanism. So here we're plotting fraction recrystallized over time, and then the JMAC analysis double log of 1 over 1 minus the fraction recrystallized versus the log of time. You fit a slope to that data, and the slope tells you something about the recrystallization mechanism. So in this case, the slope was about 1.2. And in comparison to other material systems that have been widely studied, a JMAC slope of around 1 is consistent with what's known as metadynamic recrystallization. And metadynamics, just a fancy way of saying that the recrystallization nuclei are already present in the deformed structure. The other recrystallization mechanisms, more classical discontinuous recrystallization and grain growth, may have an Avrami slope closer to 3 or 4, if I'm recalling right. But this was important here in that it's telling us that the recrystallization nuclei are already hidden somewhere within our sea of red, nominally single crystal orientations, and so we just need to find them. We did find a small incubation period, and so this analysis is actually scaled for that time a little bit. But as I mentioned earlier, as you heat the material above the beta transits, the alpha phase is dissolving, And then once it dissolves, then those beta grains become unpinned and are free to grow. And of course, that dissolution process takes time, even when you do go above the beta transits. So we did some quick diffusion calculations based on some of the sizes we measured for samples that were held just below the beta transits to estimate kind of how long it would take for the remainder of that primary alpha to dissolve once you went above the beta transits to then again unpin the beta grain boundaries, and that was of the order of around 30 seconds or so. So as I mentioned, there was kind of two competing mechanisms happening here. We had these fine recrystallized nuclei growing into a matrix of subgrains, and obviously the recrystallized nuclei are relatively clean, dislocation free, but they're surrounded by this matrix of subgrains. And of course, what makes up the subgrain boundaries are arrays of dislocations. Dislocations add energy to the system, so it's advantageous for the overall strain energy of the system for those recrystallized nuclei to grow and consume some of those subgrain boundaries, and that actually leads to a faster growth rate as compared to, say, curvature controlled grain boundary. So fortunately, in the 90s, Humphreys had caught on to the same thing and developed a relatively simple model to estimate the growth of the recrystallized subgrain, or the recrystallized grains, as they grew into the matrix of subgrains and consumed that additional stored strain energy. And then again, after some amount of time, these recrystallized nuclei that were growing eventually impinge on one another, and you transition to more of this kind of curvature controlled grain growth phenomena there. So we just plotted our data, grain radius versus time, as along with these two models, and some of the model parameters were actually taken from prior work that Lee Semyatin had done on a variety of different Ti-6-4 rods or bar stock with intentionally different textures to try to tease out the role of texture on some of the, or on grain growth kinetics. And having access to that data allowed us to estimate the mobility, the energy of the high angle grain boundaries, and allowed us to make these estimations. And as you see, the data points fall between both of these upper and lower bound models. That's not incredibly satisfying. It'd be a whole lot nicer if we could have merged these two together, but didn't quite get there. But at least it's the sanity check showing that the data points are falling within the mechanisms that we believe to be controlling the behavior. All right. A lot of the remainder of the story has to do with crystallographic texture, and so I'm going to show some pole figures and some orientation distribution functions along the way. These are some kind of composite pole figures that we produced, where the top half is showing the kind of classical representation of intensity, right? So you run the spherical harmonics and can determine what's the probability of finding grains in a specific orientation. On the bottom here, these are discrete pole figure plots where each individual pixel in the EBSD data set contributes to a set of points corresponding to that plane, so, or plane normal. So in this case, right, for 0001, each individual pixel in the data set would produce 3 100 poles on this pole figure. And that was important because I think it lets you see some of the subtlety of what's happening in the background, which is too low intensity to actually capture in the probability density representations. So I will first draw your attention to my little schematic on the bottom to try to explain what I observed, and then after that, we can look at the pole figures, and hopefully you'll see the same things here. But as I mentioned, at the shortest annealing times, right, we had this really sharp texture, very cube-like, or I guess we could call this rotated cube. since the 100 poles on the periphery of the pole figure aren't necessarily aligned with X and Y. But the main point is, starting from this nominally single orientation here, after some amount of time, we see this kind of like annular ring developing around each of the initial sharp intense 100 spots, and the intensity of the original sharp 100 texture component decreasing, and then as with further annealing time, we see almost a complete transition from our original sharp texture component to only these annular rings around there. And it's also interesting that those are, I think roughly in the range of 20 to 30 degrees away from the initial sharp orientation there. And so if now you look through the 100 pole figures, I think you start seeing that that effect, especially once you get to around 400 seconds, where we've got these rings starting to form there, and then completely have lost our original texture at 750 seconds, which corresponds to complete recrystallization. So this is just another more, I guess, in-depth way of kind of looking at that transition in behavior. I don't want to dwell on this one too long, so I have time to talk about the other things here. But I do want to just draw your attention to this plot on the lower right. So in orientation space, there's something called the alpha fiber under BCC rolling strain paths. The alpha fiber is an important one because it allows orientations to move along preferred ideal orientations with respect to that strain path. And so if I plot now just the intensities starting from this rotated cube orientation here toward the 110 type orientation over here, I can see a distinct transition where I have initially really high intensities in the unrecrystallized state. As I increase or have increased annealing time, start seeing a decrease in that intensity, and we start seeing an increase in the intensity in these kind of recrystallized regions here. So there's this transition or flow of orientations that mirrors what we looked at on the last slide. Hopefully that's not too surprising. I think everyone remembers the classical Reed-Shockley behavior plot, which shows grain boundary energy as a function of misorientation. So small angle grain boundaries have relatively low energy, and therefore they have relatively low mobility. For FCC metals, I think it's pretty well established that by the time you get to about 15 degrees misorientation, energy becomes nominally constant, except for certain special grain boundaries, sigma 3s and things which aren't represented here. And so since we were seeing this evolution, this metadynamic recrystallization process that seems to be driven by subgrain misorientations and its impact on and how that impacts their mobility depending on the grain boundary energy, we pursued using the Sparks code from Los Alamos National Lab. So this is a hugely parallel Monte Carlo code. It's got quite a bit of functionality and capability in terms of introducing different stored strains, grain boundary energy anisotropy, grain boundary plane anisotropy, like multiple phases. Lots of capability in there. So we compiled that on one of the DoD supercomputers. Had a guy, Austin, that I worked with, who's now at Ohio State, that's a wizard with Python. So he scripted everything up so we could create digital microstructures within the Dream3D software suite, and then send it directly to the supercomputer and run some simulations where we were exploring the effect of the initial distribution of texture, so the width of the texture components, and we'll see that on the next slide, but then also investigate what's the role of subgrain size on the propensity for those grains to grow, essentially trying to understand if certain subgrains had a size advantage relative to their neighbors, would that make them or was this entirely driven by grain boundary energy? And so this is a representation of the textures for a variety of initial conditions. So we created just 2D simulations in this case, although Sparks can easily handle 3D. But in this case, we created an array of 3x3 grains, so 25,000 grains in all, that had orientations sampled from the ODFs that are shown below. So we had very sharp textures with this initial rotated cube, and then we would introduce various half widths of that texture component, going to 5, 10, 15, and then ultimately we had 180 degrees, which is just a completely random texture. And we chose these constant grain, simple grain geometries just to avoid any complications in interpretation due to having grain size distribution effects. So on top of this array of 3x3 pixel grains, we superimposed 400 seed grains, and these were the ones that would have size advantages. So we had seeds with 4x4 pixels, 5x5, 6x6, and 9x9, and those all had the average value of the ODF. So they were all this rotated cube orientation. So essentially, they're probing the neighborhood effect with respect to misorientation, and then also the size effect. So here's an example from the 9x9 seed grains. So in the upper left here, you're seeing the initial condition. You can't see much, but these are 3x3 grains and here now I've thrown out all the background 3x3 grains, so you're just seeing the 9x9 grains there. As we evolve the system, in this case, because there's such a large size advantage, actually every single one of the seed grains ends up staying, and it persists through many many more Monte Carlo steps until they ultimately impinge on one another and again transition to that curvature controlled grain growth. 9x9 case is nice to explain what we did, but not super interesting. So in this case, we're looking at the case of 4x4 seed grains with a really strong 1 degree half width on the texture component in the background. So at the initial conditioning, and we see these 4x4 seed grains after 20 Monte Carlo steps. Some of them have disappeared. Others have started to grow and expand. At 40 Monte Carlo steps, we have some that have initially, I'll say we have more that have disappeared. Some which started to grow have increased in size. So the red one, green one, for example. But another one that started to grow has also kind of shrunk in size. So this blue one, and if you go to 60 Monte Carlo steps, you see, again, this blue one disappears. So things that initially had a size advantage started to grow, appear to also be able to be consumed by their neighborhood as well. So it's a complex interaction between, that seed grain as well as we determined to be like the first 3 shells of nearest neighbors relative to that, which I found pretty interesting. But in general, we're seeing that grains that develop this early at least 2x size advantage over the matrix subgrains tend to persist throughout the entire Monte Carlo simulation. This is just a graphical representation that summarizes the results for all of the different combinations. So the different line colors are the different texture half widths or line styles, I'll say. And then the 4 different plots are the different types of size advantages here. And so what we're plotting is the average grain size of the retained seed grains here. And so with really sharp textures, minimal size advantage, it's very likely for those seed grains to get consumed and disappear. Let's see, if we go all the way to the 9x9 case, in all except for the most unrealistic sharp texture, essentially that size advantage makes most of the grains persist for realistic texture intensities. and there's some kind of continuum and transition between those. So ultimately, what these simulations showed is that there is that kind of complex interplay between the size advantage, and initially we thought just the first nearest neighbors were going to be controlling this behavior, but ultimately it ended up being that the second and third shells, and so their influence on kind of that first nearest neighbor shell and its influence on the seed grain ended up being really important. So there's still more to unravel here. So this is kind of ripe for additional work. All right. So I've thrown a lot at you, so I'm going to do a quick summary of some of the key observations, and then we're going to dive into some of the effects of strain path and look at some FEM work and VPSC modeling associated with this. So we saw these abnormally large grains. I showed you the closed die forging, but by this point we had also reproduced it in side pressed billet. So just taking a cylindrical bar, laying on its side and smashing it. And then we'd also observed it in hot rolled sheet. We see that early in the annealing phase, we developed this really strong texture component that has some degree of subgrains in there. Doesn't appear that there's significant recovery that's happening, or sorry, significant recrystallization that's happening during that annealing process. But once you dissolve all the alpha phase away, recrystallization then proceeds from those grains which are highly misoriented with respect to kind of the average and dominant texture component. So yeah, I mentioned there, we saw it in side pressed bars, rollings, and the closed die forging. We were unsuccessful in producing this effect within uniaxial compression tests, and we even made a couple of unique geometries that had reduced sections, trying to introduce like shear localization to see if that had an impact. So we created kind of this axisymmetric I guess in cross section I type shape, and then we also had a plane strain compression version of that where this was extruded into and out of the page, and in neither case did we actually see any abnormal grain formation. So since we were able to successfully reproduce it in the side pressing, we wanted to take a little closer look at the thermomechanical history there as a function of location. So Air4L has a 1,000 ton forging press, and so we did a series of side press operations on 2.5 inch diameter or 64 millimeter diameter bar. The aspect ratio, I want to say, was 3 to 1, so 3 times as long as the diameter. We have a lot of experience with this and have well calibrated heat transfer coefficients and die friction coefficients, so we were able to quickly develop a continuum scale finite element model in the deform package, and then from there perform the simulations, look at local strain rate, temperature history, look at some of the flow nets, how are the grains evolving during deformation. And we did this for a variety of reductions, going from, I think, 60% all the way up to about 90% reduction. The continuum analysis is useful, but we also wanted to couple that with crystal plasticity to understand and see if primarily we could predict the formation of this rotated cube texture component. And so there we used the viscoplastic self-consistent code, also from Los Alamos, and we used this in an uncoupled fashion. So I would export the thermomechanical history from specific points within the forging, and then use that to drive the crystal plasticity model. We did get a little fancier than that, and I'll touch on that in a second there. We tried to be clever about how we introduced the temperature effects. So this is just the calibration validation of the forging, right? So you check to make sure you can match the load stroke behavior using your die friction heat transfer coefficients, and then also want to make sure you can match the the deformed geometry there. So we did that well. Here's an example of one of those side press bars where you can see right along the center line there, you get pretty extensive abnormal grain growth. It persists for some, to some distance within the bar, and then it essentially shuts off. And so that in itself was pretty interesting, and drove some of the selection of the locations we chose to do point tracking on. Used EBSD. You've seen a bunch of these already, just to check that yes, we are seeing nominally a single grain orientation within there. All right, this is where I think it gets the most interesting. So here we took an axial section. So the original bar axis is horizontal in this image, and we wanted to see to what extent did the abnormal grains go along that direction. And so we found, did these massive optical maps, and found that until you got about 4 centimeters away from the very edge of the original bar, you saw these abnormal grains. And so here's again the reconstructions, and so that drove us to choose a number of points here. So this is just again the continuum FEM solution. We looked at a variety of points here, 1 through 5, with 5 being right in the center, where we saw saw the abnormal grains forming. You didn't see them so much in 1, 2, or 3. And then similarly along the original bar axis, we went to these points that correspond with our characterization locations there. And so 7, 8, 9 all had abnormal grain growth present. 0.6 is the one that you want to pay attention to, which we did not observe any abnormal grain growth. So we took a look initially at the local strain histories. So the principal strain components along the primary metal flow direction, so that's what we're calling PMFD. The axial direction is the strain along the original bar axis, and then the forging direction obviously is the primary compression axis. From this plot, you can see a couple interesting things. So a side pressing operation is akin to plane strain compression. So it's not surprising that we see primarily strains along the primary metal flow direction and the forging direction, and relatively little movement in the axial direction. From here, we were also able to determine that locations that didn't see a strain of around 1 or so never formed abnormal grain growth. So there seemed to be a critical strain threshold. But then there also seemed to be a critical strain path threshold. So I'll go to the next chart because I think it's easier to see this. So perfect plane strain compression means that any strain I put in along the forging direction, Z here, must be balanced by strain in the primary metal flow direction, X. So in the very center of the bar, where there's no movement of that material element axially along the bar, you have a state of perfect plane strain compression. On the other hand, if we think back to my just axisymmetric upset tests, they have a strain path that's represented by this. Sorry, I forgot to tell you, L is the velocity gradient that we're going to use to drive the crystal plasticity. But in axisymmetric compression, any of the strain I put in the compression direction is balanced by equal strains in all directions in the radial plane. So that's what's represented by these 0.5s here. So you get a cylinder going to a axisymmetric pancake, essentially. And so for my various points here, I've plotted the ratio of that strain in the forging direction to the strain in the primary metal flow direction, and color coded them according to whether or not those specific locations had the coarse grain phenomena or not. We can see that all of these positions that were quite close to perfect plane strain compression absolutely had abnormal grain growth. There's this one outlier a little bit that's maybe 20% away from perfect plane strain compression, it still developed abnormal grain growth. But my 0.6 here is the interesting one, where it deviates considerably from the case of perfect plane strain compression, meaning that there was axial flow in that material element as well, and it did not show any abnormal grain growth, and believe that that's due to its impact on texture evolution. So we went to the VPSC code to try to simulate some of these effects and determine if we could predict the instances and the cases in which this rotated cube orientation would form. I realize I'm probably running out of time, so I'm not going to talk through the details of the VPSC code. Refer you to Ricardo's paper that covers it in great detail. We took well-established ratios of critical resolve shear stresses for that, and then ran both idealized models where I systematically varied the strain path and phase fraction to explore those effects, and then we did that uncoupled version with the finite element step. The one thing I did want to point out, typically these are done as isothermal calculations, but we know that in tie alloys, as phase fractions change, there's a change in the strain partitioning between the primary alpha and the deforming beta phase. And so we introduced a self-consistent strain partitioning model that Lee Semyatin had developed. And we also introduced a transient thermal analysis that would account for the effect of deformation on accelerated diffusion and its effect on the primary alpha dissolution during thermal transients during forging. And so I'm going to represent all of these results on this phi 2 equals 45-degree section of the ODF here. So again, these are the important ones, really the alpha fiber and a little bit of this gamma fiber. So we'll look at that quickly. So first thing we did was look at the strain path effect. So I fixed the temperature, I fixed the volume fraction at 25%. And over here, I'm showing my case of ideal plane strain compression. So these are the locations that absolutely unequivocally develop the abnormal grain growth. And we can see that there's, a skeleton line of intensities on this gamma fiber, and there's a pathway here where orientations are able to flow from this gamma fiber up the alpha fiber over into this rotated cube position there. If I now relax that perfect plane strain compression and I allow 10% of the strain to be accommodated along the original bar axis, I immediately shut off that pathway that gets orientations from the gamma fiber up to the rotated cube orientation, but I still am developing a relatively strong rotated cube orientation there. Now, if I go to 20%, I let 20% of the strain be accommodated by extension along the bar axis. I'm reducing the intensity of the rotated cube orientation a bit. I'm gaining a little bit of this 111, 110 texture component. So things are getting better. By the time I let 30% go, I have pretty uniform distribution of orientations along this top one here is called the 001 partial fiber, and you can see the progression. So it's telling us that there is something unique about that strain path that's allowing more orientations to get to that rotated cube than anywhere else. That's the same thing on pole figures, so I'm not going to dwell on that. Next thing we wanted to look at was the temperature effect. And so the way to do this in an isothermal VPSC calculation is just to vary the volume fraction of primary alpha. So we already looked at the 25% primary alpha case. So now we're going to look at 50% and 75%. It's interesting. It suggests that lower forging temperatures, so having 50% alpha, 50% beta, has the same impact. It shuts off that pathway to get orientations flowing from the gamma fiber up to the rotated cube, and also strengthens that 111 texture component there. And things only get better as you go to lower forging temperatures. However, nobody really likes lower forging temperatures because you need more reheats. It's more stressful on the die. and you need to replace those earlier. And so that's not necessarily the most preferred route to avoiding this effect, but it is an option. Next, I want to just show 2 quick points from the uncoupled VPSC model. So I went to the very center point here, number 5, and then we also looked at that my favorite point, number 6, which did not show any of the abnormal grain growth. And so used the exact thermomechanical history from the finite element simulation to drive the VPSC code. So we were updating the incremental strain rates as the simulation proceeded. So as strain path would change, the VPSC code would respond. And again, we were adjusting primary alpha volume fraction and strain partitioning as well. So on the left-hand side, we've got for those 2 locations the simulated textures, and then on the right-hand side are the experimental textures. For anyone who's done crystal plasticity simulations, this is actually pretty good. I was pretty pleased by this. We've got a couple spurious intensities over there, but overall we've captured a lot of the main texture components at 0.5. But the one I was most happy about, I think, was 0.6 here, where we even got the slight misalignment between 001 and the compression axis, and the fact that it had simulated kind of a this ring around the pole figure, indicating kind of more uniform distribution of orientations on that 001 partial fiber was pretty exciting. I've got like two more slides left. Hopefully that's okay. Thank you for indulging me here. So early on, I talked about the fact that there was some, at room temperature, when we look at the beta phase, we see this wide distribution of orientations, but for some reason, when we get right to the beta transis, you see only that single texture component with all of those subgrains. And to me, that was still the unanswered question, is how you went from that initial state to that state right at the beta transis that then gives rise to all of the abnormal grain growth and everything that we're trying to avoid. So if you can fix that problem, then the abnormal grain problem doesn't come around at all. So just like many things, when I start thinking about a problem that involves crystallographic texture, I went to the literature, and of course, Dirk Rabba had already done some work there, as had Tony Rowlett. So those are two of my favorites that I really enjoy reading their papers. But some of the key things, this was already discussed and has been observed in other BCC metals as well. So it's not unique to titanium. This rotated cube orientation is or can be problematic in any BCC transition metal. And some of the reasons that were outlined for this was with respect to the plane strain compression strain path, there's very limited driving force for crystallization. That's a highly stable orientation that doesn't require a lot of dislocation activity or work put in to remain stable, and so it tends to prefer recovery over recrystallization. The other thing that highly symmetric orientation with respect to plane strain or rolling does, makes it so it doesn't develop strong orientation gradients. So measurements of rotated cube-oriented grains in single-phase materials show essentially like no internal misorientation, whereas everything else around it has all these little subgrains forming. Further, the slit planes that actually are active in that orientation have very little elastic interaction between them, and it's also been observed that those subgrains can be consumed by the recrystallization front of adjacent grains, just like we saw here. Or that the highly misoriented subgrains themselves may be the nuclei. So yeah, we saw both of those. All right, as my last slide here, just want to have a quick comment on on the so what. Why after we did all this work, what did we do that was useful with it? One, we made a presentation that was intended to be given at the ASIP 2019 conference. Unfortunately, that ultimately didn't happen. But the good news is it did public release some data that allows me to talk to you about it here today. So we started with all those subscale lab trials that we just saw on the 1,000-ton forging press. Working with Lockheed Martin and Arconic, we actually scaled that up and repeated a lot of those experiments on billets of much larger size, so 8, 10, 12 inches. We also did side pressings at a variety of different initial aspect ratios, which allows you to play with it, kind of tune that amount of plane strain compression versus amount of relaxation, I'll call it, where you allow the axial direction to extend as well. We developed a user subroutine in deform that took into consideration that that critical strain. So you need to have a strain of about 1, but it also had a pretty cool way of aggregating the number or the amount of strain that was put in with plane strain compression. So we had kind of 2 clocks running, and if both of those critical conditions were met, you would find the subroutine calls out locations in the forging where the strain was high enough and it was close enough to plane strain compression that you may have a problem with abnormal grain growth. So that gives forging designers a tool to try to develop a preform shape and a forging strategy that avoids the abnormal grain growth. Everyone's heard the crawl, walk, run thing. So we did the crawling with the lab trials, and then we tried to just run like the 50K Ultra, I'd say. We looked at an actual structural forging that consisted of 302 steps plus a closed die forging. So this was a hand forging operation, and really hand forging means there's a guy driving a truck with a hydraulic manipulator. Someone else is running the forging press, and the person with the manipulator is adjusting it, moving it forward, back, so they can take bites on the forging and then move it around to work it into the shape that ultimately goes into the closed die step. So we painstakingly watched videos of that forging, measured the die opening on each step, cataloged it. It was 302. I can vouch for that. And then created a deform simulation of that entire thing, including the closed die forging step, and attempted to validate that deform user subroutine on that actual part, which was pretty neat. I'd say overall, nominally successful. I don't have any of the graphs from that one, unfortunately, but in this part, this is what we saw on the early ones as well. You would see kind of right in the location my mouse is on both sides. It would persist for a while, but then this was about a 3-foot-long forging. As you got far enough down the forging, just like we saw in the side pressing, it would shut off. The abnormal grains would shut off, and we were able to predict that relatively closely. So in addition to that subroutine, we also just came up with those rules of thumb, like, don't try to avoid plane strain compression, and if you're going to do that, don't put in strains greater than 1, which led to some revised strategies for some of those early forging operations. You call them either preforming or blocking. And at the time, within a couple of years, we'd reduced the rate of occurrence of this roughly by about 20x. So I realize I went long. Again, thank you for indulging me. This was like one of my favorite things I worked on while I was at the Air Force, so it was fun to go through the story again. I will leave the conclusions slide up here and then entertain any questions if time permits.
Thank you so much, Adam. There is time for us. If there is time for you, then we will definitely take some questions. And it was, I must say, it was really wonderful to hear this. It's like a full circle. I'm sure it is very satisfying when you solve a big industrial problem with all these state-of-the-art techniques. But also it's all metallurgy, which is really close to my heart, that it is truly traditional metallurgy at work. So I was really delighted to Listen to you. And Deepa is here, I think, with the first question. So I'll go ahead
nice.
with her first.
Yeah, first I have to apologize for jumping back there. A bee just like flew and is like crawling on my laptop. Oh no.
Okay.
All right.
Hey, Adam, how are you? Good to
I'm
see
well.
you.
How are you doing?
Hey, finally,
Yeah,
I'm
likewise.
seeing you. It's so strange. Hey, thank you so much. I'm sorry I got caught in traffic, so I joined a couple of 10 minutes late, missed the initial part. So, personally, thanks for giving this fabulous talk. So, this is contemporary, or is this some part of your PhD or something like that?
Oh, yeah. This was, I want to say 2016. There was a number of forgings being rejected, supporting an Air Force program. And so the system support folks took a look at it, couldn't figure out what was happening. So they called in the lab guys, and we described it as forensic metallurgy a little bit.
Okay.
To try to
Sorry, I
look at the
missed that part.
microstructure, see what was unique, and then I don't know if you caught this part of it, but when we took these initial EBSD scans, it reminded me of samples that Lee and I had prepared like even 5 or 7 years before that, which we thought were worthless. They were just in a drawer somewhere. But as soon as I saw this data set, I was like, those samples are going to tell us the progression of what's happening. So.
Okay. Thank you. I mean, I was just wondering, what is the timeline, that you had for this kind of an effort? So, was it over a couple of years, or how do people hold off on that supplier? Since Jaya said that it was really nice to hear the transition, I thought the audience
Yeah.
here will, you can give them a little bit of perspective. I'm personally interested in that as well.
Yeah. So I'd say like 2016, the problem came to us by like 2018. We had those kind of general recommendations of don't exceed a strain of 1 and avoid plane strain compression at all costs. And then there was probably another 3 years worth of work where we said, well, now let's go back and let's play with the Monte Carlo simulations. Let's do a little more VPSC work, and let's do the upscaling work with Arconic and like Lockheed. But yeah, we'd already kind of made those rules of thumb within 18 months or 2 years or so.
Sure. Thank you. I'll hold on to some couple of other questions I had. Let the others ask.
Sure.
Yeah, Karthikeya. Next.
Okay. It was a really nice talk, Dr. Adam. One of the elementary doubts which I had was regarding one of the DA by DN versus DK curve, which you showed in the starting. Yeah. Although, like, I can understand why you have removed the numbers, but still I wanted to understand how do you actually measure the crack length? Like, this is one of the problem which I am facing. So what was the approach you used to measure the crack length?
Sure. These were classical ASTM compact tension specimens with direct current potential drop method, but then also a traveling microscope to look at the surface crack length. So the potential drop method or the potential drop measured crack lengths get corrected to match the actual observed optical crack lengths. So that gets you these. What I didn't show here explicitly were any small crack growth measurements. And so if that's something that you're pursuing, I'd say there's 2 ways I've done it. The first one is really painful, but is using acetate replicas. So it's kind of like Scotch tape. You soften it with acetone, stick it to the sample, and capillary action draws it into the crack tip a little bit, and then it hardens, and you have put it on a glass slide, and you can look at it under an optical microscope to make those measurements. We did that for many years, but then more recently have set up optical systems to try to capture to do this with like high resolution digital cameras. And there's now some nice convolutional neural network algorithms out. Trying to remember the name of it. It's like crack CNN or something like that, but that allows you to very easily segment the crack from the image data and develop pretty good measurements of crack growth rate. The downside with the small crack measurements, or it's not downside, but just a fact of running those experiments, is you need to make some estimate of what the aspect ratio of the crack is. So like the surface crack length is interesting, but ultimately it's the one going into the depth of the material that's important, and that which you would use for any sort of like life prediction calculations. So it's good practice there to do a couple experiments to certain crack lengths, and then stop the test, certain surface crack lengths, and then stop the test, and you can like heat tint the material to make that a different color and break it open, so you have a real clear witness mark of what the aspect ratio was at a couple different crack length increments.
Okay. Thank you. That really answers my question, and I will look it up, this crack CNN neural network model. Second question which I had was that you mentioned that in the Monte Carlo simulation, there was a abnormal grain size reduction in 4x4 matrix, seed matrix, which you gave, 4x4 seed matrix. So there the seed matrix actually reduced in size. But how do you rationalize that? Because either the size reduction must happen through a recrystallization of new grains, but the original grain having reduction in size, how do you rationalize that? Yeah, in this one.
Oh, yeah. So you're saying like, why do some of these disappear?
Yeah, why do some does disappear? Like some, yeah, that's actually my question.
Yeah. So I wish I had like a higher mag version of this, but so well, I might have the equations hiding somewhere. Yeah, so the Monte Carlo simulation, each Monte Carlo cycle, every pixel is changed, flipped to some other orientation, and then the question is asked of the simulation: did that lower the overall energy of the system? And a lot of that is driven by curvature of the grain boundaries. And so in these cases, every one of those seed grains had the same orientation. It was neighbored by some other set of grains, and that first shell of neighbors has a second shell. So even those subgrains are evolving, those, the first, second, third shells. And so if some grain in the first or second shell of neighbors, if it is able to grow to a large enough size, it can then consume the original seed grain. And then I really wish I had like a graphic to show this better, but I do not have it at my fingertips. But remember that, let me see if the paper has anything better in it. Yeah, that's not going to help either. But yeah, so remember that the seed grains were all the average orientation. The subgrains in the background were all sampled from those different ODFs. And so it's possible that two of the matrix subgrains had some high misorientation, making those boundaries pretty mobile themselves. So it all has to do with, it's just a competition between the grain boundary energy and mobility of the seed grain versus its nearest neighbors. That's probably the best I have right now without having any more detailed graphics. Apologies.
No, thank you. That's actually that's making much more sense now. One more last question which I had, I probably missed it. You might have said it, but did you use this Monte Carlo simulation model in your FEM studies also? Like you use the output from this, or that's a separate study?
No, this one was kind of off on its own. One thing that we had always wanted to do, so Spark's code also has a phase field simulator in it. And if I go back to my now I lost it. This one. Yeah. One thing that I'd always wanted to do that we never got around to doing was to try to simulate the dissolution of the alpha phase and the growth of these underlying beta orientations. So Sparks definitely could handle that, because you do like a phase field step and then a Monte Carlo step, phase field, Monte Carlo, which would be, I think, really interesting. But yeah, I have never linked it with the FEM work.
Okay, thank you. That's all from my side.
Thanks.
Yeah. Ratnesh, you go next.
Hello. It was really very splendid talk. I wanted to know something about KZMA analysis regarding the reversion of austenite. And can you suggest me some paper or some book so that I can refer and to incorporate these things in my study?
I'm sorry, could you repeat that one more time?
Hello, sir. I wanted to incorporate KZMA analysis regarding the reversion of austenite in the merging state. Like you have shown certain things you have incorporated. So how can I incorporate? Can you suggest some book or some papers regarding this?
For recrystallization kinetics, I think there was a JMA model that JMAK analysis. This is not KZMA.
Oh, okay. All right. I was like, hazy. Yeah.
Is this? Yeah, that's what I was also confused. Is this the one, Ratnesh, you're talking about?
Yes, ma'am. Yes.
Okay. Yeah.
Yeah. Okay. So my favorite paper there is there's a Roger Doherty paper. Well, it's a whole bunch of people, but it's the best review article I've ever seen on recrystallization and grain growth, and references all sorts of other papers that might lead the way. So let me I can send that, and maybe you can forward it on for me.
Surely, yeah. Thanks a lot, Adam.
Yeah. No, that's definitely where I would start.
Yeah, Roger has visited us many times as well.
Okay.
Because Professor, one of his students is a faculty at IIT in the Dev Samajhdar, so he does a lot of EBSD work as well.
Yeah.
But yeah, we will look him up. I think that's something that should be easy to find. Thank you.
Okay. Yeah, this is the one.
One more thing regarding, like, sir, you have compared
Noted.
effective in-boundary energies versus the misorientation. So, like, can it be incorporated through experimental model, either without doing any POTS, like POTS model you have used to get these things? Can I get these things through experimentation?
Yeah. So can you get the grain boundary energy and mobility through experiment? Yes. They're, I'd say, very difficult experiments to do. So Tony Rowlett has a really good paper on this. They go through it for thin, it's some sort of, like, I think aluminum, like thin foil, but the hard part is you need to have grain boundaries that are basically perpendicular to the surface of your sample, because the way you derive these energies and mobilities is you look at the correlation between grain to grain misorientation, grain boundary curvature right near triple points, and then the dihedral angles between grain boundaries. And from those measurements, Rowlett and I mean, I don't think he developed this technique, but like he's the paper I'm familiar with, but they've come up with a way to, or shown the way at least, to then reduce that to grain boundary misorientation or grain boundary energy and mobility. We actually tried to do that. Lee Semyatin started doing that probably while I was still an undergrad. He created a sheet with really large beta grains and then cut it, trying to ensure that the grain boundaries were perpendicular to the surface. It was a 12-inch by 12-inch sample. EBSD was done on the entire thing, both sides. The grain boundary curvatures, dihedral angles, everything was measured. This was over the course of like 20 years by like multiple different students and postdocs, myself included. And I provided the last piece of the puzzle, which was the grain boundary curvatures. And then we had also applied my reconstruction code. So we had really good measurements of the beta phase orientations. And then a postdoc that I had tried to get it across the goal line. She was very computationally savvy and ultimately determined that the grain boundaries in our sample were not perpendicular enough through the thickness to make the assumptions that go into reducing the data. So we got nothing useful out of it. But what I will say is for BCC metals, this curve is definitely shallower. This is pretend that that's a smooth curve, but I would say that the for BCC, the Reed-Shockley equation, assuming the critical angle is like 30 degrees, is probably the best estimate that I have right now. And there's also, while we were working on this, there was groups at Manchester in the UK, and then in France as well. I forget the university, but they also made some nice observations. And the French group also was doing Monte Carlo modeling and ended up using something like around a 30-degree critical tolerance angle here as well. And it makes sense with respect to some of the where we're starting to see these big peaks of intensity in the recrystallized grains as well.
Thank you, sir. That was
thanks for the question.
Thank you.
Yeah, that was very detailed answers to those questions from students, in fact. So thanks, Adam. I also had a couple, if I may ask, if you have time. So you talked about changing annealing. The time it takes for this transformation to occur in the beta, when you just take it just about the beta after the deformation. Did you also change the extent of deformation? I mean, you talked about, of course, the strain path changing, but did the extent of deformation also make a difference too?
Yeah, definitely. And I did go over that part just too quickly.
I'm sorry,
I realized I was getting
that.
out of time.
Yeah.
No.
Okay.
Yeah. No, I definitely, thanks for bringing it up because I didn't really say it. So when we caught on that side pressing was like the right strain path, we actually set off a master's thesis by now he's, I think, Captain Lee Morris. So he did a thesis at Air Force Institute of Technology, and he looked at far more variables than we did. So he explored, we had done 3 reductions, but he looked at a variety of reductions for various RAM speeds. So looking at strain rate effects, and then also looked at some of those kind of like top hat shaped and I-beam shaped specimens that I alluded to. So this was the critical plot here that I didn't really mention, but so this vertical line here, and I guess it's funny that it's as a function of foraging time, but it's ultimately tied to strain. So no locations, no abnormal grain growth was observed for locations that experienced a true strain less than 1, regardless of path. That doesn't matter how it was put in. So true strain of 1 does seem to be a critical condition. Our smallest reduction was like 56%, or maybe it was like 60%, something like that, and never saw it in that sample.
Great, thank you. And I think my last question was probably not about the work that you showed, but you mentioned some in situ EBSD heating experiments by some other group possibly. But would you know whether, because things happen very quickly here, so would you know how they did those measurements? Yes, I think it was this particular reference.
Yeah. So they looked at a relatively small area, and they were doing I forget if it was like, 2000 frames per second EBSD or something like that. So they were a small area, pretty fast rates, but the video was amazing. I saw it at the 2019 World Thai Conference, and it showed exactly what we were saying about these rotated cube subgrains are like, they're just expanding at the expense of all the other beta phase orientations, like concurrent with the alpha phase dissolving. So yeah, they have a nice set of papers out on that. I don't know if the video ever got uploaded as like supplementary information, but like the video, like,
beautiful. Yeah. Yes, I can imagine.
Yeah, like I wanted to do that experiment so bad, and nobody had the heating stage for me to do it.
Right. Yeah, we missed that too here. So, but yeah, it's true that the in situ tools are very dramatic in ways how we can see what's happening.
Yeah,
useful tools. Yeah, I don't see any other raised hands. But Deepa, do you want to say anything more, or do you have questions? Deepa, you're muted.
Yeah, thanks, Adam. This is truly a pleasure to listen. I think some reason, I mean, I know many more people would have been interested in this, but there was some glitch in the link, joining link. In fact, I myself, so a lot of people working here on Titanium, Dipankar's group is also there. So there was some, so thank you really for joining us here. And on behalf of all of us here, we'd like to see you in India for the SIC 2024 in October. So,
I hope so.
Yeah, Professor Raghu Prakash is there, Jaya is there. So we will send you a formal invite, and I think you should give several talks there.
Yeah, yeah, this can be broken up into at least 4 talks, I'm sure.
Yeah. I mean, I'm stunned. It's almost 4.5 years, no? The whole root cause analysis, and not at all trivial to find this kind of solution. So really appreciate, it's really phenomenal. So see you in October, and good weather in India and Nagpur. And
Sounds
you need
good.
any help from us in terms of invitation, visa, letters, early bird, and please put in your papers with whoever is the MP leader now, and please join us in India.
All right. Yeah, Bob Grillotti is the new MPE executive. Bob. Yeah.
I see. Okay, please tell Vasish. I think Vasish also we've invited. So you must come, really. We're not taking a no for an answer.
As long as we get travel support, that's the.
Yeah, he was just mentioning it in the beginning.
Okay.
Yeah.
Right.
But hopefully that will relax before then.
Yeah.
So.
We keep our fingers crossed as well on that.
Yeah.
Yeah. In fact, I just started. Also, we sort of started working with Peter Anderson at Ohio State as well to do some modeling experiments. So yeah, I think there are some visits scheduled. So I really hope that we can meet in person and discuss more. But thank you so much, Adam, for a really in-depth presentation. I really enjoyed it.
Yeah. Very nice.
Appreciate
it. Have a good weekend, and thanks for staying early for us.
Yes.
Oh yeah, no problem. My pleasure. All right. Take care, everyone. Thanks for the questions. Bye.
Bye-bye. Thank you.